Right, this is our first discussion of the semester on GIS. So this is our getting started with GIS PowerPoint lecture discussion from Module 1. And we want to frame what GIS is and how it works, and talk a little bit about the software, the data, some of the functionality. We'll do a little demo. We'll do some different things throughout this PowerPoint. So how GIS works. GIS provides tools for working with geographic information. So there are tools that allow us to find geographic information, create geographic information, manage, maintain, share, analyze. So they're the tools that allow us to work with this GIS data or geographic information. You're going to start to hear a lot of terms. Often hear that taking your first GIS class is a lot like taking a foreign language as far as the terminology that you have to learn. Lots of new vocabulary and words. A lot of what makes it a little bit more confusing even is that a lot of the words are interchangeable. We use different words that mean the same thing. Geographic information is a good example. The geographic information are the layers of GIS data that we use to model the real world. So we'll call it geographic information. We'll call it GIS data. You'll hear it referred to as spatial data sometimes. And all of this stuff has always been referred to in the GIS world as layers. Layers of data that we use to overlay and make our maps. Okay, so GIS provides tools for finding, using, creating, and sharing geographic information. A GIS uses hardware, the computers, software. In this case, we use ArcGIS primarily. QGIS is a free and open source software that we mentioned as well. Quantum GIS or QGIS. So we use hardware, software. The data is really important. The data are abundant. Sometimes it's free. Sometimes it costs money. Sometimes you have to build it yourself. Sometimes you can get some and then you have to update it. So the data is a big part of what we do and use. Okay? The data, the GIS data, or the geographic information, the spatial data, the layers, all of that, the data. The data are very dynamic in the GIS world. It changes a lot. So we spend a lot of time keeping it up to date and maintained. Of course, people are still in the loop. We have to be here to keep the computer plugged in, at least. Hopefully there's more for us to do at our job than that still these days. We have to keep the data maintained. We have to use the data to better do our job, to answer questions, to better manage the world around us. In addition, we have a bunch of workflows that we use to help us keep the data updated, processes that allow us to integrate this technology into our work and better do our job. So simply put, a GIS is just a tool for creating and using geographic information. That's it. That's a pretty straightforward definition. The second bullet there is what we used to say more often, a tool that integrates hardware, software, data, people. I like the third bullet down there. It's just a tool for creating and using GIS data. Right, that's all it is. And the GIS data is a big part of it. So it's a spatially enabled database management system. So a database management system, and these days we use a lot of relational database management systems that are a series of tables of information that are connected in a way that reduces redundancy in a database, and it makes it more efficient. So there are databases everywhere. We use databases every day, whether you know it or not. I've probably used this example in the first class. When you go online to an online store to buy something, like Amazon.com for instance, and you want to buy some toothpaste, and you got to decide on the brand of toothpaste, so you do a drop-down list and you pick Colgate. And then you got to pick the flavor, and you do a drop-down list, and there's 20 flavors, and you pick the flavor. Then you do a drop-down list, and you pick the size tube you want. On Amazon servers, there's tables of information that store all this stuff, and it filters through all those tables and provides you a result. All right, so database management systems are used to manage everything from the inventory at Lowe's to the stock on Amazon.com, to a patient database at a doctor's office. So databases are used these days to manage large amounts of information. There's nothing new about databases. A GIS is just a database, but it has this front-end map. So just like the database on Amazon that stores all these different types of toothpaste, imagine we had a database of trees, and it's just a table of information about a bunch of trees, say on our campus. We might have a column that stores the tree's common name, maybe the genus and the species, maybe the diameter at breast height, maybe the condition of the tree, information about trees on campus, the height of the tree, things like that. So that's just a table of information, like a database storing information about trees. What the GIS does is it also incorporates the location of each tree. In this case, the location would be an individual point or a pair of coordinates that defines where that tree is in the real world. So a GIS is a database management system, but it's got this front-end map on it. So it ties the database information about features in the real world, like trees or manholes or roads or buildings, cities, streams, to actual features on a map. When you are using the acronym GIS, please use it whether you are please use just GIS whether you are referring to a singular geographic information system. We will use a geographic information system in class, or whether you are referring to plural geographic information systems. Geographic information systems are used throughout cities all across the United States. So GIS are used across cities across the United States. Don't say GISs, please. It's the point of that. Okay, so what can you do with the GIS? A GIS uses geographic information to help answer questions and make decisions. So here are some of the things that we can do with the GIS. We can simply map location. Maps that are just really map location are referred to as general reference maps. It's a whole class of maps, and we've got an example of them here somewhere, maybe. This is just these screenshots are right out of your Esri training course, and this PowerPoint goes along with the Esri training course. So the stuff you hear me talk about today will be reinforced when you step through the Esri training. So this is a map showing parts of Africa. It's just a map that shows location. We can also map quantities. This particular map shows percentage of females in the population in 2010. This map is made up of polygons of counties and states. The database information that lies behind this map is census information. So we can map location, we can map quantities, we can do things like map spatial relationships, things like what's inside of what's contained within other features. In this case, we're looking at crime data across counties in Florida and school locations in relationship to those crimes. In one of my other GIS classes, we do a little assignment where we download a neighborhoods polygon from the city of Asheville. You download a layer of neighborhoods in the city of Asheville. And you can also download Asheville crime data that's updated daily. It's point data. You can download the crime data. And the crime data shows you all types of crimes. I think they take out some of the crimes. But one of the things that we do with that data is out of the crime data, there's a field that defines what type of crime, and so we pull out the graffiti, all the graffiti locations, and we determine how much graffiti there is in the 5 Points neighborhood. So we've got all the neighborhoods, and then we've got all the graffiti, and we've got all the crimes, and you can select out of all the neighborhoods one neighborhood, and then you select out of all the crimes one particular crime, and then you look at how many of those crimes are within one other polygon. So that's a pretty common kind of process analysis that we do with GIS. Things like population density can be mapped. We have a lot of census data available. things like proximity, what's closest and nearby. This is looking at potential spending index and some type of store. Last night in class when we were doing this lecture and discussion, someone asked, well, where does all this data come from? Who owns the data? Who makes the data? There's a ton of freely available data from government organizations, cities, counties, federal, state. There's a lot of private data that gets built as well. A lot of private data is available for free. There are license restrictions on some data, and some data cost money. So looking at this layer makes me think about some data that costs money. Looking at something like spending potential index, that's a data set that some company built and sells as a business product to help stores know where to locate. So census data I mentioned is freely available, and there's a lot of it. When it's the basic census data is free and easily available, but when you start looking at the more detailed census data, all the information that's collected during a census, that data doesn't get built out in a way that's really easy to use. So some companies will download all that data from the government, and they run a bunch of processes on it to make it more useful and easier to use. They do a bunch of value added stuff to the data, and then they resell it. So the census streets data is a really good example. The data that comes from the census is a good example of the United States Census Bureau. They've been building GIS data for a long time, and they've built it to help them better do their job, to count people in the country. And then they make that data available because taxpayers pay for it anyway, right? So their street centerline files are called TIGER data. TIGER. Topologically Integrated Geographic Encoding and Referencing, I think is what that stands for. Free streets data for the whole country. And back in the early 2000s, the late 90s, I was using it, and the data was pretty incomplete. But if you wanted to get streets data for a county, a lot of counties didn't have GIS data then, you'd get it from the Census Bureau. And you'd have to build it out and make it better. That data, there were a couple of guys at the Census Bureau who developed the TIGER standard. They developed this way to encode and build out the streets layer. They left the Census Bureau, and they started a company called GDT, Geographic Data Technologies. And the exact sequence of these companies and the numbers are a little foggy in my brain at this point, but these guys took this freely available data you could just download, and they actually created the whole standard, and they started making the data better. They had these guys, they had some people working with them, I think it was in the Northeast, and they were downloading all the TIGER data, and they were making it better. They were adding to it and making it better. And so they started selling these street centerline files. GDT eventually sold to TeleAtlas for in the billions. TeleAtlas sold to Navtech for in the many billions. And those were the roads layers that you saw in all of the internet mapping sites like Google Maps and MapQuest and all that stuff. Where do they get their streets layer? They bought it from GDT. That turned into TeleAtlas. That turned into Navtech. And so that's a good example of how some government data that's freely available, someone started taking the data and making it better and selling it, and it turned into a multi-billion-dollar industry. All right. So we can map change as well. This shows population change across the country. The darker areas have greater change. When we make maps, when we symbolize our GIS data with different colors, we see darker colors as being more. So just glancing at that map, I know that the darker green areas are going to be more population change than the lighter green. So you want to play on how people interpret data subconsciously when you make a map and you symbolize a map. And you want to think about those kind of things. It's easy to make a map that misleads people without trying to mislead people. So population change, something else we can show. All right, so we're talking about geographic information and GIS data. We typically store our GIS data in two common data models, the vector data model and the raster data model. These data models are used in industries and disciplines beyond GIS. We're all familiar with raster data, so let's talk about it first. Raster data are data that are built as a gridded cell structure. Each individual cell in the file is a pixel. The size of it defines the resolution of the file. Every time you take a picture with your phone, a JPEG is a raster data model, is a data format that is part of a raster data model. So JPEGs are raster data. Any image is raster data. In a GIS, we use raster data to model things like, raster data are how we store aerial photography, but we also use raster data to model things in the world that are continuous in nature, that don't have a definite starting and stopping point. Things like temperature, precipitation. So the temperature in this room at 69.3 right here, and well, it might be if we go down to enough decimal places. It's not 69 right here and 70 right here. Right? Temperature's a gradient across the landscape. So we use raster data models to model things that are continuous in nature. Places like NOAA and the National Climatic Data Center, that is now called the National Center for Environmental Information, I think, here in downtown Asheville, they store all of the weather data that's ever been collected in the United States, in that federal building downtown. They get in the like 20 or 40 terabytes of data come into that building a day. A lot of the data that they have is raster based. They look at a bunch of climate and weather data. So they do a lot of raster based stuff. Vector data is data that we use in a GIS to model things that are discrete in nature. So if you're going to create a layer, a GIS data set of buildings on this campus, buildings have definite starting and stopping points. They are distinctive. They're distinct. So we would use vector data to draw lines that outline a building shape. Right? So vector and raster data. We'll talk a little bit more about it, but I want to make the point that vector and raster data are used in other disciplines, like I said, like when you take a picture with your phone, you get raster data, JPEGs. That doesn't have anything to do with GIS, even though your phone will tag that long with your pictures now. That's another discussion. But how about Adobe Photoshop? Anybody ever heard of Photoshop? Photoshop a picture? Photoshop works with raster data. That is Adobe's raster software. Adobe Illustrator, vector. Adobe Illustrator works with vector data. It works with lines and points and polygons. No one is, well, some people use Illustrator to do some mapping stuff, but most people are doing things like making company logos in Illustrator. Right? So vector and raster data are used commonly throughout a lot of industries. In the GIS world, what makes it GIS data is that we tie it down to the world using coordinate systems. So coordinate systems or map projections are really important with our GIS data, and we'll have a whole module that covers that. All right, so a little bit more on vector data. Represents distinct locations with precise location. We use different geometries depending on the object that you're trying to represent. So we build all vector layers in a GIS from these basic building blocks. We have points, lines or polylines, and polygons. Points are defined by a single location and represented as a pair of geographic coordinates. The things in the real world that we might model as points are things like trees, manholes, light poles, maybe a city on a map might be a point. Polylines are defined by at least two connected pairs of geographic coordinates, things like streets, rivers, power lines. And then we have polygons. Polygons are lines that close on each other, things like city boundaries, buildings, and lakes. Just because we model something as a point one time doesn't mean it might not be a polygon another time. and this has to do with the scale you're mapping at. If you can imagine a map of Buncombe County about this big, let's say 30 by 30, all right, a map of Buncombe County. If we put cities on a map of Buncombe County this big, you might imagine that you would see the outline of Asheville and the outline of, how are y'all looking, Black Mountain, right? You see polygons. So on a map that is zoomed in, that's large scale, shows a smaller area. Large scale is a relatively smaller area. You show more detail. And cities on something like that would probably be shown as polygons. If we showed the same on the same size piece of paper, 30-inch by 30-inch, the entire United States, still can't, California, East Coast, the entire United States, and you put Asheville on that map, do you think you would be able to see the outline of Asheville? On a map like that, the scale is different. It is a larger area, it's a smaller scale map, and cities are probably points on that map. Okay, so just because cities are points one time doesn't mean they won't be polygons another time. It depends on the scale you're mapping. Vector data are the type of GIS data that has the database tied to the back end of it. So you can click on one of these types of vector data on a map and see the information associated with it. In a GIS, we call that information that describes the points, lines, or polygons, we call that information attributes. It's the tabular, non-spatial database information that describes those points, lines, and polygons. Now, some more terminology, and I should have mentioned this on the first slide. When we talk about points, lines, and polygons, some more terms used interchangeably. When we see points, lines, and polygons on a map, we refer to those as features. The features on a map. Attributes describe features on a map. That database information describes features on a map. You'll also hear them referred to as geometries sometimes, just to further complicate the situation or confuse the situation sometimes. A lot of vocabulary. So these points, lines, and polygons are geometries, they're features, and we have database information that describes those features. In the GIS world, we call that database information attributes. So attribute information can be accessed through the attribute table. These tables are organized by rows or records and columns or fields. Each row will describe an individual feature, like a point, such as a bird sighting. The column provides information about features. The columns can store different types of data. You can store text, or numbers, or dates. That's just like a database. When you design a database, every field in the database, you have to tell it what it's going to store. Is it going to store text? Is it going to store numbers? Is it going to store numbers that hold decimal places or whole numbers? Is it going to store dates? Is it going to store, you can store other things in databases these days, like videos and images and all kinds of other stuff. So how you define the information that's going to be stored is important, because if you store, let's say we wanted to look at the height of all the buildings on campus. We wanted to look at the average height. So we had a field for the height of each building. But we stored that field as a text field, and we plugged a bunch of numbers in there. The system's not going to let us look at any mathematical kind of functions on a text field. It's got to be a number field. So you can store text, you can store numbers in a text field, but you can't do any math on them. So you got to think about how you store the data in the database. And that's all kind of database concept stuff that we'll hit on as we go through this. So attribute tables are a lot like a database management system. What makes GIS different than database management systems, other database management systems like Microsoft Access, is this tying together or linking of each feature on the map to that database information in the background. The GIS spatially enables a database management system. It doesn't spatially enable Microsoft Access. A lot of these data formats, these GIS data formats, are they are built from the ground up by companies like Esri to be able to store, analyze, maintain geographic information. All right, so raster data is better suited for modeling objects or phenomena without distinct boundaries. It's a data model that defines surfaces as an array of equally sized cells arranged in rows and columns. A raster's origin, cell size, and relative location are used to determine location of cells and the raster on Earth. Each cell in a raster does store a value, but it's a little bit different than a full attribute table you see when you click on a point, a line, or a polygon. When you click on a cell in a raster data set, you will usually just see one individual value. If you're looking at something like a digital elevation model, which is a raster-based data set that models elevation, elevation's continuous, it changes all over the place, the value you'll see is elevation. If you click on a cell in a color aerial photograph, just like a picture of the Earth taken from a plane, the value you're going to see is a value of R, red, green, and blue. Color in a computer is made by mixing light of RG and B, and so you'll just see a value of RGB, which isn't super useful. That's not necessarily. A lot of times, raster data is just used as a background. All right, so how about all this data storage? Gaining a good understanding of all the data formats that we use in a GIS is important. There are a lot of data formats, and we all use data formats all the time. These are going to be some new ones that are a little bit different than ones you're used to using. What are some common data formats you all use already? Text files, right? PDF files, Word documents. Do you all use those, right? So data formats are what we work with in a computer. A data format allows the computer to store information and then display it back to you. Data formats work along with a piece of software that creates that data format, and the functionality in a software is tied directly into a data format, like a Word document. And you can do all this fancy formatting, you can insert images, and the ability in Microsoft Word to insert an image is tied directly to that data format that the two are built together. GIS data are no different, except they're a little different. The different thing about GIS data is your operating system doesn't really understand the GIS data. If you download a GIS layer from Buncombe County's website, you download it and you unzip it and you go double click it, your operating system is going to not know what in the world to do with it. Okay? Data formats in your operating system there's a file association with that .txt that tells what software to open it. File association. The file association doesn't get set up with the GIS data formats. It's a little bit beyond what most people do at a computer, so it doesn't quite work that way. So raster and vector data can be stored as a variety of data types. The vector data types can be stored in a folder or as a file-based format like a shapefile, or they can be stored in a geodatabase as a geodatabase feature class. Raster data sets can be stored in a folder, or you can store raster data also in a geodatabase. Esri has some specific data formats that they've built to allow their software to do some really powerful GIS-y, geographic information kind of things. The shapefile was built a long time ago in the late 90s, and it was awesome, and it still is awesome. You still see a lot of shapefiles. If you go to Buncombe County's website and you download some GIS data, you're going to download them in shapefiles. It has become the de facto data transfer standard for GIS data. You see a lot of them still. It's an older data format though. It's not as powerful and can't do as many things as their newer data formats like the geodatabase or the GDB, which has feature classes in it. So you'll see shapefiles and geodatabases this semester. If you are working in the Esri world, the geodatabase is a really good way to work. You get a lot of functionality through it, and it can do a lot of things that other data formats cannot do. If you are going to be giving your data to someone to look at in CAD, or if you want to give your data to someone to look at in a free software program like QGIS, shapefiles are easier to use across many different platforms. Okay? There is a trend towards open formats, open data formats, KML, GPX, PostGIS, WFS, WMS. All of these are open data formats. Open data eases the use of data across different platforms. And these days, with things like the internet, open data and the easy exchange of information across different systems is really important. That's really valuable to people. The old model of software was to, the old business model, like Microsoft's business model, was to make a piece of software and make your data format only work with your software. So if people started building Word documents, they had to use your software. These days, people are trying to get away from that. There's a lot of initiatives with open data. There's the Open Geospatial Data Consortium, an organization that keeps up with all these standards. And what do we mean when we say it's open data? It's not tied to any particular vendor software in a way that the software vendor or whoever develops the data format makes the standard open so you can look at how it's built. So you could build your own piece of software that creates these data formats. They're not tied down in a way that you can't even figure out how the format was built. So Esri is committed to open standards. If you can't see my air quotes, if you're listening to this PowerPoint, they say they're committed to open standards, but they kind of drag their feet really opening the geodatabase up fully for other people to write software that allows it to access the full functionality of the geodatabase. The geodatabase is really powerful. And in Esri's defense, they've built ArcGIS with this geodatabase format to do all this really powerful stuff, and it's hard to imagine someone else even being able to build a software that does all the stuff Esri's software does. So it's kind of natural that you build a piece of software and your data format has to support all the things you want your software to do. So there are some open data standards, and these are some of the standards. Now, in the Esri world, in ArcMap, I said the shapefile was built long ago. When they came up with their latest version of software, ArcGIS, it's been a while now, but they came out with a geodatabase. So ArcGIS and the geodatabase has been built from the ground up together. The geodatabase is like the native format for working in ArcGIS. You can easily work with shapefiles in ArcGIS, but if you want, we'll see some of the advanced functionality I keep talking about, but we'll see some of this stuff as we move on into the semester. The geodatabase is a great way to work if you're working solely inside of the Esri world. Couple other mentions of at least one of these. I like to mention what KML is because everyone knows what Google Earth is. Okay, KML and KMZ are the data formats for Google Earth. Google Earth was a program called Keyhole before Google bought it. Keyhole was the code name for the first spy satellite program in the United States, and so Keyhole, they named this program after because it allowed you to look at the Earth with all this imagery and data. So KML stands for Keyhole Markup Language. It is it's a tagged, it's a lot like HTML. It's a markup language. You can open the file and easily read it. It's a human readable data format kind of thing. All right, moving right along. How about metadata? What in the world is metadata? Metadata is data about your data. What in the world does that mean? So if we wanted to download some data, let's just look at Buncombe County GIS. Here's the download digital data page. You accept the terms, and here's a bunch of GIS data we can download directly from Buncombe County. And it's nice, they have metadata here available. So the metadata, when you download data, what the metadata should tell you are things like, when you download a parcels layer, it's nice to know the last time it was updated. Is this parcel layer from 2007, or was it updated yesterday? Parcels change every day. Property is bought and sold every day, so the database attribute information changes, and parcels are subdivided or parcels are merged together every day. The data changes all the time, so knowing the last time it was updated is valuable. That would be in the metadata. Knowing how it was created. Was it created using a GPS on a phone, or was it created using a survey grade GPS? What attributes come with this data? What does it have the owner of the parcel, or does it just have the size of the parcel? What attributes are available? A big thing that you get out of the metadata is the coordinate system information. Coordinates allow us to overlay data together, and coordinates are really important. So knowing the coordinate system is really valuable. So things like that you find in the metadata. All right? Metadata is really important. Metadata is often incomplete or non-existent. It is the last thing people go to do in a project, and it's oftentimes there's not money or time to do it or do it well. Outside of school, I build a lot of data for my own projects, and I don't build a lot of metadata for them, unfortunately, but a lot of the stuff I build is just for me, and I use it for my own projects. But you know, next year somebody might say, oh, you did that great project, would you share that layer with me? I say, sure, I'll share the data with you. Next thing I know, they're calling me every day saying, well, what about these attributes, and what's the spatial reference, and when was the last time you updated it, and how did you create it? So metadata gives information about the data. State, federal, county organizations are required to provide metadata by state regulations, which is good. ARC Catalog has tools for creating and updating and viewing metadata. There's a lot of other tools to do it. A lot of people will just create a text document describing the data, and they'll provide it with the data. So they don't use any real tool to build metadata. So often missing or lacking necessary detail. Metadata. All right, so layers. We work with layers in a GIS. GIS maps are organized by layers. What are these layers? These layers are the geographic information we've been talking about. When you hear us using the term layers, it's a generic term. It doesn't matter if we're overlaying an aerial photograph that's a grid format, that's a grid data, that's a raster data model, or a JPEG, or a TIFF, or a shapefile, or a geodatabase feature class, or some CAD data. They're all just layers. Okay? We just refer to them all as layers. It's just kind of a generic way we talk about layering data in a GIS. It's been that way forever. We've been talking about layers in a GIS for a long time. So it doesn't matter what specific data format we're talking about, what kind of geographic information. I will talk about add a layer to ArcMap all the time. And you're either adding a shapefile or a geodatabase feature class or a DEM or an aerial photo. A map layer references the GIS data. So we're talking about layers, and their underlying data is what it references. We use layer symbols to represent collections of features, And a layer is comprised of features that are similar. All right, so in a GIS, layers are thematic. We do not put dissimilar things in the same layer. For instance, we might want to make a layer of manholes on this campus that would be a point layer, and we make a layer of trees. Those are all points, but we don't put them in the same layer. They are different kinds of things. They are in different layers. They also have a different set of attributes. The trees all have a set of attributes like name and height and genus and species and condition, and the manholes have a different set of attributes, whatever we want to store about them. Layers can be turned on and off in your GIS and reordered. We will see that. Normally, you want points on top, then lines, and then polygons. In ArcMap, the way things are ordered in the table of contents is the same way they're ordered on the map. By default, all features in a layer get the same symbol. When you load a layer into ArcMap, they all look the same. Okay? For instance, the trees on campus. I load a trees layer into ArcMap, and let's say there's maples and oaks and pine trees and elms. There's all kinds of trees, right? When we load it onto the map, they're all points that look the exact same. Through the symbology tools, we could symbolize oaks to be a little red dot and pines to be a little green dot, based on information in the attribute table. So we can symbolize things to look differently based on the information in the database. We can also label features based on the information in the database. By default, again, everything's the same when you put it in, and then you have to symbolize it. So attributes that represent things like the name of trees are categorical. They are non-numeric. Attributes that represent categories of things, like a school type, can be displayed with different symbols, colors, and more. Attributes that represent numbers and values can also be symbolized in different ways, but we do things like different size symbols based on the number, or a color ramp based on the values in a table. For instance, that population density map we saw. These polygons have a field for population density, and that field, the numbers in the field have been broken into different classes, and each class has gotten a different color along a color ramp. So this is an example of how you can symbolize numeric data. And let's see, mapping. Don't have a good example of non-numeric. That's numeric also. We'll come back to the non-numeric. So your attributes, the attribute values can be numbers or non-numbers, categorical or quantitative, and the way we can symbolize and use those vary based on whether they're numbers or not. All right. Well, I'm going to demo this in just a moment. Okay, so scale is important when you're making maps. Scale determines the level of detail that you can map. Scale is the relationship between the size of a feature on the map and the actual size of the feature in the real world. We can express scale in a lot of different ways. The most common worldwide way is expressed as a ratio, or also referred to as a representative fraction. 1 to 24,000 is a good example. When you see it expressed like that, this means that a feature on the map is 24,000 times smaller than its corresponding feature in the real world. So when you see it expressed like 1 to 24,000, what this means is that one unit on the map is equal to 24,000 units on the ground, whatever unit it is. If you measure an inch on a map, it's 24,000 inches on the ground. That distance is 24,000 inches on the ground. If the map's big enough to measure a foot on the map, it's 24,000 feet on the ground. The units are the same in the numerator and the denominator. It's a fraction. It's actually 1 over 24,000. Okay? Now That's what that means. So that's a common scale for a USGS topo map, 1 to 24,000. So we talk about large scale and small scale often, so let's look at that. Large scale and small scale. I said, and in our classes I will say, a large scale map of a small area. I say these things together all the time to help people understand. Small area. Large scale, small area. Small scale is a large area. And it gets confusing. I saw the chief of the North Carolina Geodetic Survey talking about a neighborhood small scale map because it was a small area. And he's talking about a neighborhood. Small scales are large areas. This guy's got a PhD in geodesy. Right? He knows the difference, but talking to a room of people, he said that. And that's why it gets a little bit, people get confused about it. One of the reasons. Well, let's look at really what it means. All right. So when you say a small scale map, see, when you say a large scale map of a small area, 1 to 24,000 is a reasonably small area. It's a large scale map. 1 to 100,000 is a larger area and a smaller scale map, because 1 to 100,000 on the ground, 100,000 is a bigger area than 24,000 on the ground, right? Starts to make sense when you start to see it like that. When you write it like a fraction, it really starts to make more sense, because that number, 1 divided by 1 million, is a smaller number than 1 divided by 24,000. Right? So small scale, large scale. That's a ratio or a representative fraction. You see it expressed like that often. Another way we see scale represented is expressed as equivalence, as it says here. I usually call that a verbal statement of scale. 1 inch equals 1 mile. And when I was back when I was first doing GIS, or even before I started doing GIS, I used maps a lot before I was even working with GIS. I always liked verbal statements of scale. 1 inch equals 1 mile. Because I know what an inch is and I know what a mile is. It just made more sense to me. The longer I've used maps and the longer I've worked with GIS, I see a representative fraction and I know exactly what it means. You can convert from one to the other easily. If you know that 1 to 24,000, if you say, okay, well 1 inch equals 24,000 inches. All right, well what does 1 inch equals in feet? Well, you know there's 12 inches in a foot. So 1 inch on a USGS topo map that has a representative fraction of 1 to 24,000, an inch equals 2,000 feet all day long. Okay. We often see scales. We see this representative fraction a lot too. 1 to 63,360. And at first glance, you're like, why in the world would you put that as a scale of a map? There are 63,360 inches in a mile. That equals 1 inch equals 1 mile. On the maps I make, I put that and I put the verbal statement. And then I often will make a scale bar that shows in miles and one in kilometers. So you can put them all on a map, depending on the map I'm making, but I will also often include more than one representation of scale on a map. All right. So 1 to 63,360 is 1 inch equals a mile. A paper map has a fixed scale. A GIS, you can zoom in and out, so the scale's dynamic. The other thing I want to mention about scale on paper maps, if a paper map is shrunk or enlarged, the scale bar, the representative fraction changes. Scale's not the same if the map is shrunk. The scale bar changes with it. Scale bars always stay true. If a map is shrunk, the scale bar shrinks too. But the representative fraction is wrong then. So you have to be careful about that. And I've had students come to me with maps. They had a student came in with an 8.5 by 11 map, and it had a stream on it with a buffer on it, and they were doing some kind of stream quality they were looking at something within a stream buffer, and he was like, I really want to recreate this buffer. How can I draw it? And I was like, why don't we just use the buffer? There's a buffer tool. You can say buffer this stream by this distance, and it makes the buffer. But there was no scale on the map. This map had been changed in size, and it was difficult to figure out what size buffer was on the map. So there are ways to determine scale by measuring between real-world features and things, but it's a little beyond the scope of this class. All right, so scale is important. People don't understand scale at all. People will ask you to make a map of Buncombe County on an 8.5 by 11 piece of map with all the roads labeled on it. Okay, I want an 8.5 by 11 map of Buncombe County, the whole county, and I want all the roads labeled. You can't do that. The bottom line is because of scale. The scale of the map is why you can't do that. Scale is determined by the size geographic area you're mapping and the size piece of paper you're mapping on. So if someone tells you they want Buncombe County mapped on a 40 by 40 piece of paper and they want it zoomed in as large as it'll go, the scale is what it is. I mean, it's the size of Buncombe County. You're not going to change the size of Buncombe County, and if they are mandating you be on a specific size piece of paper, then the scale is based on that size geographic area and the size of the county. Buncombe County is pretty neat. It maps at 1 inch equals 1 mile on a 40 by 40 inch sheet of paper. 40 inches is about what most plotters do. Some go up to 44. So that plotter back there does 42, I think. So most cities and counties have a plotter about like that one back there, and the biggest map they print is about 40 inches. And so they want to put their county as big as they can on a map usually, and Buncombe County's nice because it happens to be 1 to 63, 360. When I say people don't understand scale, a lot of people just don't. They really don't. I worked with an engineer for years on doing sewer rehab work. He did the rehab, and I helped him with the maps. And he told me one time, he was like, I want this sewer, I want it on a map as big as you can make it on this piece of paper, and give it to me. And so I did, and the scale ended up being 1 to 47,858 or some weird scale because I zoomed in as much as I could. I didn't try to get at a specific scale. And he called me and he was like, what's wrong with this thing? The scale's not right. And he had an engineer's scale that he was trying to measure on the map with. I was like, well, you told me to make it, you didn't tell me to make it a scale. You told me to make it as big as I could on this piece of paper. So, but he actually told me the scale was wrong because it wasn't a scale that he could use with an engineer's scale. And I mean, he knows a lot about maps, and he's an engineer, but he still couldn't quite, the scale thing was still throwing him off. So it happens a lot. Data view and layout view. In ArcMap, in our GIS software that we use to make maps, we use data view when we're adding, editing, and analyzing data. When you go to make your map, you switch to layout view. Layout view is like your page view, and it's where you insert your title and your scale bar and all that stuff. We'll see that. Finding information with information tools and attributes. There's an identify tool that you can click on features on the map, and it will show you the attributes. You can also open the table in and look at it. I'm going to do a quick demo here and show you some of this. Because we have a database, we can query that database. So database management systems allow us to query. Maybe we want to select out all the trees that are greater than 20 feet tall, or all the trees that are name equal pine. Okay, so we can query information out of our attribute table with a database query. It uses SQL, structured query language, a common database language for interacting with databases, just like Access and every other database uses. ArcGIS is nice. It's got a little GUI that builds that SQL for us. We don't have to build SQL, write SQL by hand. This is where GIS separates from the database management system. Because we have the spatial component, the geographic component, we can also do location queries. In addition to just selecting out things in the table by query, like select all the trees that are greater than 200, also tell us which ones fall inside of the AB Tech campus. So we can do intersections, look at how close something is, near, adjacency, inside. So this is doing location queries is what breaks us away from normal database queries, and the two can be combined in the GIS. We will do a lot of queries in this class. Alright, stick with me for another 5 minutes, and I'm going to do a quick demo. In here, ArcMap can be loaded by clicking the icon down there in the taskbar. I will fix that error. It opens up with your Getting Started window here. You can open an existing map, or you can do a blank map down here, or where's the blank map? Or you can just cancel it to start a blank map. If you've used Google Earth before, you open Google Earth and you see all this information. ArcMap, no information. So I'm going to add to this map using the Add Data button. I've got some data on the server that I'm going to load in our Asheville folder. I've got a geodatabase here. Inside a geodatabase, what you see inside a geodatabase is all of these individual things are referred to as a feature class. That's a specific geodatabase term. Generically, we could call them layers. These are layers. I'm going to load them into ArcMap. You can see some are points, some are polygons, and some are lines. So I want to add the county boundary, the French Broad River, primary roads, parks, Blue Ridge Parkway, municipalities, national forest, parkway boundary. And let's just see what it looks like. By default, ArcMap puts the points on top, then the lines, and then the polygons. It doesn't know which polygons should be on top of which other polygons. Like the parkway boundary should be on top of the county boundary so you could see it, and so should the municipalities. Okay? So you order things so that they're ordered in a way you can see them. The county boundary, it might be nice. You can click right on the symbol there. I can make it hollow, and I can change the outline. So there's a lot of things you can change. If you make something hollow, it doesn't matter if it's on the top or the bottom. Let's put the French Broad River. Let's make the national forest. By clicking right on the symbol, you can easily change the color. Alright, now let's turn off a couple of things. You can turn layers on and off to make it easier to see. And this is your Tools toolbar. We are currently in Data View. We could change to Layout View and see Buncombe County on an actual map. Let's go back to Data View. Our Tools toolbar allows us to zoom in and out and pan on our data. And we can also identify. What is that polygon right there? It is Black Mountain. It's got this set of attributes. A lot of times you see attributes that don't really mean a lot to you. This data was built by someone else some other time, and those attributes probably make a lot of sense to that person. Alright, how about this little thing there? What's that little polygon? No, there's no municipality name associated with that. I'm not sure why that is. How about up here? Montreat. Wouldn't it be nice if these polygons of the municipalities were symbolized differently based on what municipality it was? We can do that by going to the layer properties, right-click a layer and go to the properties, and there is a symbology tab. When we load a data layer in, everything gets a single symbol, like we mentioned. All the municipalities, all the polygons have a single color. We can also symbolize it by categorical data, non-numeric, like the municipality name. Tell it to add all the values that are in that field. Apply. There they are. So we're using table, attribute information in the table to symbolize. If we had numeric data, we could do it by graduated colors or symbols, all kinds of other stuff. We'll see that later. All right. Now, it's important to understand that there's this one-to-one relationship, for the most part, between the features on the map and the information in the table. A point layer is a good one to look at to understand. So everybody see this parks layer? That park right there is Warren Wilson College. So they've got soccer, and a lot of parks are actual schools too. How about that one right there? Carpen Fields. It's a county park. All right. So if we were to want to see all of the attributes, we could right-click that layer and open the attribute table. And there we are. So for each park, there's all these attributes for each one. A lot of times it takes a while to figure out what in the world all these attributes mean, because you didn't build the data, you downloaded it from somewhere. Maybe you built it, but if you downloaded it, it takes a while to inventory and better understand the data. The point I'm trying to make is that the number of records in this table, 110. There are 110 records in that table, which tells you there are 110 points on this map, which tells you there are 110 parks in this county, based on when this data was created. It could be 10 years old. Maybe there's 3 new parks. Who knows? All right. So that relationship between this table and the features on the map is important to understand. You can select a record in the table, Malvern Hills Park, maybe. It lets me. Oh, East Riverside Park. If I select it in the table, it's selected on the map. Okay. So I have 5 parks selected. I selected them in the table. There's 5 selected on the map. You can also select them on the map using this select tool. Oh, I selected the county boundary too. So 1 selected out of 110. That's Cane Creek Pool and Fields. Okay, so these features on the map and the attributes in the table are connected. All right, and there's usually a one-to-one relationship. There can be these multi-part polygons, multi-part features, like Hawaii has a bunch of, if you click Hawaii in a states layer, it'll select all the islands, but just one record will be selected. So there are cases where there are multi-part features, but generally this one-to-one relationship is a good way to think when you're just learning how this data works and is connected. All right, so that's vector data, points, lines, and polygons. I want to show you really quick raster data because we've got a great example of it here in North Carolina. I like showing it, and then we'll take a break. So raster data, equally sized and spaced cells. Digital elevation models are a really good example of this. We've got DEMs for the whole state, high resolution, built from our floodplain mapping program. Our state's flooded a bunch of times. In the early 2000s, they started flying high resolution LiDAR data to build out better floodplain mapping data to mitigate floods and to plan for floods. And so we've got great elevation data. I'm going to load 2 raster data sets. You can see the icon here is a little gridded cell structure thing that tells you it's raster data. And this is what it looks like. This is called a shaded relief model, or a hill shade, and I like it because it looks cool. I like seeing things looking like this in 3D. This is Asheville. Right here is Carrier Park. Right here is AB Tech. This is the Swananoa River coming into the French Broad River. Pretty nice. High resolution stuff. The resolution of these pixels, if you zoom in enough, you'll see, you can even measure it. 20 feet by 20 feet on the ground. Okay. When I started mapping in North Carolina, the best digital elevation models you could get were 30 meter by 30 meter, 90 feet by 90 feet. So the data's gotten a lot better, and it's really a visually nice thing to look at. I like to show it. You can even see like roads in here. You see things like this. You might know what that is right there. That's the 240 cut right between Charlotte Street and Tunnel Road. That's the tunnel right there. Go in and see that little tunnel. That's where the tunnel starts. How about that right there? Anybody know what that is? That is also that mountain. That's where they dump that mountain when they cut through it. So when you do something like that, you got to put that earth somewhere, and they put it right there. I never knew that until I was showing this one day. I was like, oh, that's what they did with it, and it totally is. I remember they always said they were never going to build on it. Now there's stuff built all over that. There's stuff up there now. In the past 10 years, they've built that out. This is raster data. That layer was actually built from this. This is the actual digital elevation model. If you click on a cell here, what you get in the pixel value is the elevation. That pixel I clicked is 3,726 feet. Okay. From this digital elevation model, we built a shaded relief model, or a hill shade. People look at that and they think they should be able to click it and get elevation. That's actually is a reflectance value of the sun. The sun, you build this by saying the sun is somewhere in the sky at a certain elevation, and it casts shadows on it to build this. You can also, from this digital elevation model, that's what they build slope from, aspect. You can model flow and drainage from the landscape because it goes from a higher cell to a lower cell. So you can do a lot of neat stuff with digital elevation models. I like to, you can symbolize them pretty ways, like with elevation, and make it where you can see, make this one transparent so you can see that elevation through it. You can get some pretty nice effects pretty easily combining these things. Of course, we don't have snow-capped mountains around here all the time, so you can modify that symbology a little bit to change it to show min and max, and change the max to be something higher than there is in that. So that lower, so then it pushes the white out of the color ramp. So some different techniques you can do. This is our reservoir. Where we get our drinking water. Yep, that's the North Fork or Burnett Reservoir. That, which is that the one right above? Is that the one right above Leaf? Is it Lake Eden? Is that where y'all's is? There it is, right there, right? Yep. So that's the mine he works at. Okay, that's a little demo. That's some talk on GIS, and appreciate y'all paying attention. We'll do another one next week.